Hello everyone, I'm back with a new episode of the solid state physics course. And in this case, I'm going to expand on the G space or the reciprocal space formalism. In the last class, we saw that for periodic properties of the periodic crystals, which are having discrete spatial symmetries, discrete spatial symmetry allows the crystals properties like the electron density, the matter density, and all of those things to be periodic in nature. And periodic functions, as we know from the last class, can be decomposed into various Fourier components, and it can be represented as a in a like dual basis, which is not the position basis that we are like normally using. It's the reciprocal basis, which is a dual basis of the normal basis, and this function can be actually represented there also by the help of Fourier transform. So this is something that we looked upon, and we completely described it from a mathematical point of view. So we described the mathematics of it. Now we are going to see that why should physicists come up with such an idea? Like, I mean, it's very ad hoc. It seems that this kind of ideas, the G-space parallelization, like the G-space formalism, that seems very um, like ad hoc, and we don't know the significance of it until and unless we know the motivation. So today in this class, we are going to discuss the physical motivation that motivated physicists to actually uh, think that something like G-space formalism or the reciprocal space might exist. Like it's not existing in reality, but it can exist as a very useful and strong mathematical tool to describe the solids, the periodic properties of solids. So we will start with a very nice example. So all of the experimental proof of G space or the periodic properties of the materials come from something known as crystallography. So what is crystallography? Crystallography is basically bombarding a substance. So you take a crystalline substance. You take a crystalline substance, you bombard with some electromagnetic waves or some things, some external particles, and so you get some result. So the particles actually scatter, and you measure that how the scattering looks like. So that will give you an idea about what is the internal structure of a crystal. So basically, it can be related to wave optics. So for understanding this class, you must have a little bit of wave optics background. So you need to know the basic concept of wave optics. So for example, we know diffraction or we know interference. So for example, we have a double slit experiment, which is called a Young's double slit experiment, and we have a screen. So we have a Young's double slit experiment in which we have a screen and we have a double slit. So this is the red line is a wall from in which there are holes, two holes. So let's say light is coming and it gets bent. It gets bent. So let's say this angle is theta and this angle is same for both of the lines. So this is very small. We have to assume that this is very small and this is angle theta. So the depending on the wavelength of the light, the distance d and the theta, we will see bright and dark spots in the screen. So let's say the path difference of these light beams is this much. The path difference is this much. So let's say we name it A, B, and O. So the BO light is covering more distance than AO light. By how much? By so it will be, let's say this is theta, this is D, So it will be d sine theta. The extra distance is d sine theta. Okay. So the extra phase. So basically in each wavelength, the light actually moves around the whole phase. So if you draw a phase diagram, then we will see that the light moves in the phase. So let's say the phasor is called it measures the phase. So the phasor moves like this because light is a wave. So the phasor moves like this. You need to know a little bit of wave optics and like the wave nature and the how the waves work for this for to decipher this. So a phasor is rotating, and if you translate it, if you see it uh, in the distance covered, so every lambda distance, the light will go a full circle. It will cover 2 pi phase. So for this much extra distance, it will cover this much extra phase. And if this phase is an integral multiple of 2 pi, then we will have constructive interference. So these light and this light will add up. So we will get a bright spot. But if it is and not an integral multiple of 2 pi, but like an odd multiple of pi, then we will have destructive interference because the first phasor will be like this, the green line, the second phasor will be like this, the pink line. So they will cancel each other because the phase difference will be pi. This odd multiple of pi. So the phase difference of pi means that they will cancel each other. So this is the principle of interference, and this can be also extended to something called diffraction, and that is exactly what happens in a crystalline surface. So diffraction is also like, for example, let's say there are not only one slit, there are a lot of slits, and it will follow the same rule as the interference. So d sine theta has to be equal to n lambda. So this is the um, for example, this would be the condition for constructive interference. So what we will do, let's say, what we do is, so what in the crystallography, what is done is a very nice thing. So, for example, mm, you have a crystalline surface and you keep it at an angle. So you keep it at an angle. So angle theta, for example. So you shine a light and it gets reflected. So if this is at angle theta, if this is an angle theta, what will be this angle? So this is an angle theta. So the angle of reflection will be 2 theta. The angle of deviation will be 2 theta. And now we will measure this in a screen. And for certain angles, this condition will be satisfied. And we will see bright spots on those angles. So basically, excuse me. So basically, we will rotate the crystal from 0 degree to 90 degree, and which angles give us a bright spot that we will see. So we will track this light which is coming for a particular angle theta, and we will keep it such that the angle is for the inclination of the crystal is theta and the angle of the detector is 2 theta. So we will keep it like that, and for every such theta from 0 to 90 we will actually see that what is the profile, what is the brightness. If we see a very bright spots, we know that this thing is being satisfied. So that is the basic principle of crystallography. So it's also called Bragg's law. So we will see this. So points. There are points like this. So let's say these are the um, interplanar distance d. So a light is falling like this with an angle theta, and on the light is falling like this at an angle theta. So we can see that the extra distance that the lower beam covers here, it will be d sine theta. So this will be theta. Okay. So a little bit of mishap. Yeah. Sorry. This is not theta. Rather, this angle is theta. Yeah, this angle is theta. So this is d sine theta. This is also d sine theta. Sorry for this mistake. This is not theta. Rather, this is theta. This upper angle is theta. So d sine theta, the extra path is 2d sine theta, and that has to be n lambda. Okay. So this is called Bragg's law. So from this, we can actually estimate the interplanar distance. If there are multiple interplanar distance which are periodic, so for example, there can be multiple planes in which we can see a periodic structure. So we will see multiple thetas where there will be peaks in the curve. So when we actually, when the crystallography is done, so intensity is plotted with respect to theta, and we will get a profile like this. For certain angles, there will be sharp peaks. So these angles, if you actually, uh, if you actually plot this, if you actually see, then you can decipher that what are the different Ds that are there. There can be different Ds, and there can also be different multiplicities for same D. So let's say there is a single D. So 2D sine theta is lambda, 2D sine theta is 2 lambda. So this will give us two different thetas, and we will get peaks in two all of those thetas until unless this is followed, and we will also get different Ds. So there is like a multiple crystal planes are there in a crystal. There are multiple Ds in a crystal, and so like you have to be very careful about deciphering and analyzing all these things. Okay, so this is one of the like key features of crystallography, which affirms that there is an underlying periodic structure. So now in the next class, we will study another method called Lawes method, Lawe condition. And this Lawe condition, we will connect it with Bragg's condition. This is called the thing which we studied is called Bragg's condition. This is called Bragg's condition. So Bragg's condition and Laue condition, we will take these and we will see that, okay, so now the motivation for reciprocal lattice, the reciprocal space representation emerges. And that's how physicists got very interested and they got motivated that, okay, that this reciprocal lattice representation can be a very useful and crisp mathematical way to describe crystalline systems. So that's for it for today. We will, in the next class, we will meet with new methods, for example, Laue method. Until then, see you next time.